Okay, so I'll now develop this idea a little bit further. One thing is that I can say that it's possible to show this algebraically if you let x be 0.333 recurring. Then I should just say this is part 2 of my talk about limits. So here we're saying that 1/3 we can write it as 0.333. We can view that as a geometric sum of 0.3 plus 0.03 plus 0.003 and so on. So algebraically, if we start with this value and then we multiply by 10 on both sides, then the decimal point will move 1 unit to the right. And then if we take 10x minus x, then all this 0.333 will just, subtract and become 0. We'll just be left with 3 here. So we get 10x minus x is 3. So this is 9x is 3. We get that x is equal to 1/3. So that is another way to see that. Here you see I have this written out as a table. And if we're going to write this algebraically, then we can say that the limit as n approaches infinity of this sum that we're calling Sn, that limit is 1/3. And the Swedish for limit is gränsvärde. Okay, so what I thought I'd talk about next is this example from page 39 of our books, where we have this function given by this formula. So it's a rational function. So really this is why we learnt about rational functions in the previous section of the book. It's so that we can talk about limits. Okay, so for this rational function, then it's not defined for x equal to 1. So the domain can be all real numbers except for x equals 1. Okay, because we cannot divide by 0. So that means that we cannot find the f of 1 directly. We cannot evaluate this formula when x is 1 because we cannot divide by 0. Okay, but we can use limits. Okay, so really this is the main point of limits. The limits are used to find values that we can't find directly. It's kind of an indirect way to find such values. Sorry, I just thought I'd zoom in a little bit here. So let's see here. So when you take that, this formula, this expression, you substitute n values for x. So we can think we're evaluating that function at different values for x. Then, as shown at the top of page 39 in your books, then the values are 1.9, 1.99, 1.999. Okay, and if we take values that are slightly greater than 1, then the values are 2.001, 2.01, and so on, 2.1. So what we can say is that as x gets closer and closer to 1, if x is less than 1 and it gets closer and closer to 1, then this value for f of x is getting closer and closer to 2 there. And if x is greater than 1 and x approaches 1, it's getting closer and closer to 1, then the f of x is getting closer and closer to 2. So then we say that the limit as x approaches 1 of f of x is 2. Okay, so we cannot evaluate f of 1 directly, but we can find a limit, and this is often very useful. Okay, so let's just have a look at what we could do algebraically. So this x squared minus 1 here, we can factorize this as x minus 1, x plus 1, using the difference of two squares, which in Swedish is called konjugatregel. And then we can cancel this factor x minus 1. So we get that f of x is equal to x plus 1, where x is not equal to 1. And then we can say that as x approaches 1, as x gets closer and closer to 1, remember that x cannot equal 1, but we can get as close as we like to 1, then that means that x plus 1 will get as close as we like to 2. So then we say that the limit as x approaches 1 of x plus 1 is 2. Okay, so here we've shown it algebraically as well. So this was part 2 of my talk about limits. Thanks for watching.